So our fifth talk in the sequence this week of lectures on geometrical numerical integration aspects of dispersive equations for quantum mechanics is by Alexander Ostermann on low-regularity time integrators. Please.
Well, thank you very much. This is the title. It was already announced, and I'm going to report on this because this is something I've been working during the last years. So my interest is in integrating dispersive equations where the initial data and hence also the solution has very low regularity. This joint work with a lot of people. They are named here, and well, Chunmei is here in the audience. Katharina was already here.
And we'll be here next
We'll be here next week again. So let me start with an example. And I start with an example which is well known here. It's the Nonlinear Schrödinger equation. And I'd like to show you that whenever you apply a standard method, and I will show you two standard methods, one is splitting and the other is an exponential integrator. Whenever you use these standard methods, you run into problems when you don't have enough regularity of the solution. So let's first do splitting, because splitting is, I think, one of the favorite methods for most people working in this field, and that person is here sitting who has done the paper already in '86, or when was it, on that topic. So splitting consists in, splitting up the equation into two equations. So I identify here a linear part, which is minus I times the Laplacian if I multiply by the equation, and the nonlinearity. And then I integrate both of these equations separately. Well, this sounds fantastic. It is fantastic because both of these parts you can almost solve exactly. The linear part you can solve in Fourier space, and the nonlinearity, well, for this you have an exact solution. And with that, after a time step, a small time step in general, you combine these two solutions to get an approximation. So this is the way how it works. As I said, you split up and then use these two individual flows, you combine them, and the simplest way is to do least splitting in first order method. The question is, what do we need in order to prove convergence for that? This seems to be simple whenever A and B is something small bounded, but in our case, don't forget that A is an unbounded operator, so I times the Laplacian, so you have to be a little bit careful when you just say this is clear that this is first order. So let's have a look on that. I know that some of the people in the audience know how this now works, but give me 5 minutes, I explain to you how this can be carried out, I think in a quite simple way, and by this you immediately understand what you have to require for the solution in order that this least splitting I propose here is really first order. So what we are doing an error analysis in terms of the, I call it mild solution. So the integral equation you get just by integrating here the differential equation. I'm doing this because, well, here the object, as I said, in particular the A, they are very nasty objects, unbounded operators, where here then the operators are quite nice. These are the evolution operators. So this is a bounded operator, nice object. So I write down here the variation of constants formula, the mild solution, and then the trick is to reinsert iteratively the solution you have here on the right-hand side. This is still the unknown solution. You iteratively the same formula. Well, here for least splitting, we do this just once. This is enough. So if I introduce for the U of S here, again the same formula, I get here the first part, which comes from the linear part of the equation. And then the second part I can easily estimate, because this is an integral here of size tau. And the contribution that I omit here is also an integral of size s, which is smaller than tau, and all the other operators such as bounded operators. So what I can do just a simple Taylor-series expansion. So what I get is such a formula, such a representation of the exact solution, whereas the numerical solution has this form, And here I have to be a bit careful. Of course, I should never expand this e to the tau a into a series. As I said, a is unbounded, but I can do this with the b. B is a bounded object, so I just expand the exponential here, get this simple formula, and then I have to compare. I have to compare the exact solution with the numerical solution, where the first term is clear. If the first term would not be the same, then consistency would even be a problem. First term is the same. But well, for the second term, what most of you, or maybe all of you, immediately see is that, well, this of course is an integral, but what is written down here is just a quadrature rule for this integral. If you put the, or if you choose the node s equals 0, what you get is just this as the evaluation of the integral. So this is the application of a certain quadrature rule. The quadrature rule is given here with the error term. And what we want to have is that the method in total is a first order method, so the error should be tau square. So the difference of these two terms also should be tau square. This would be perfect. Then this splitting would be first order. So this term has to be tau square with the f. Even here is the f. Well, we compute f prime. And what you see, there's a simple calculation. When you differentiate with respect to s, once here, once there, you get a commutator of b and a. What you need is that the commutator applied to the exact solution must be a bounded object. So this requires spatial smoothness of the solution, because this commutator is a differential operator. So you differentiate the solution, and still it has to stay in the space where you do the analysis. So this basically, this idea goes back to Christian Ludwig Tobias Janke, who published this in 2000 in a very nice bit paper. So when we apply this now to our nonlinear Schrödinger equation, the cubic nonlinear Schrödinger equation, well, you have to do the analysis, or I should say the algebra here. You compute this, and you can believe me, or you repeat in a few seconds what you get here as a term is the Laplacian, so in one dimension, the second derivative of u. This means that whenever you want to estimate the error, say in a certain Sobolev space, you need two additional derivatives of the solution. The solution must be 2 times more differentiable than the norm in which you measure the error. So this is some additional regularity you need for the solution to get first order. For Lie, you can do or carry out the same calculation of a Strang splitting, and you find the second commutator. You do the algebra, and you see 4 additional derivatives are required.
I think with full generality, you're absolutely right. But if A is a Laplacian, B is multiplication per potential, I think you need
Sure. Of course, but for this case here, for this nonlinear,
for nonlinear.
Yeah, no, I say here for the nonlinear.
For nonlinear.
Of course, if you have a particular potential, it can be different. You're completely right. Well, you might say then maybe splitting is not the right method for such equations with low regularity. Why don't you use exponential integrators? This is quite a natural question, because I've worked so many years on exponential integrators, so I should have used exponential integrators. Maybe the exponential integrators are much better. So again, what would an exponential integrator look like? So when I like to solve this equation, again, I start with the mild solution, Duhamel's formula, or I call it variation of constants formula, given in that way, and then exponential integrators. They rely on the idea that the bounded object which is in here can easily be computed by an explicit method. For instance, here simply by explicit Euler, which means that instead of the unknown u of s, I just take the initial value u0. This is the simplest numerical method. I just continue with the initial value as a constant. Well, if you do that, you see that you can compute the integral, because this is like just a constant vector, a constant function. And well, you get a certain, integrate this, but the primitive is well known, this function here, which we call phi1. And then you get such a formula, which at first sight looks a bit strange, but well, for the nonlinear Schrödinger equation, when I write down the formula, it takes this form, and this can be computed very easily in Fourier space, because in Fourier space this operator diagonalizes. So with fast Fourier transform, of course, this product here I have to compute in physical space, but switching between physical and Fourier space, I can easily evaluate that. At least when, say, that the domain is, well, the torus or something simple. But again, if you're doing the analysis, and maybe you see it already from the requirement that, of course, un plus 1 should be close to un for small step sizes. If you want to have this requirement, well, this is of size tau, so this should be close to that. If you do an analysis of this using the expression here, what you find is that this red part here is un plus something order of tau. But again, this is only of order 1 if the Laplacian of un is bounded. So again, you need 2 additional derivatives. And I think you can carry out this game with all the standard methods. You always see that you need additional derivatives. Well, there is still a hope. The hope is that, well, this is maybe the analysis done with whatever, triangular inequalities, etc. Maybe this is not sharp. So let's do numerical experiments. And when we are doing numerical experiments, you get this. Well, I have to explain a little bit what I'm doing here. So these are double logarithmic diagrams, I think. Or is there anybody in the audience who has never seen this? This is not the case, I don't have to explain what I, yeah, okay, then I explain. So this is a double logarithmic diagram. I'm plotting here the step size I'm choosing, and I'm plotting on the y-axis the error or the accuracy I get after the integration. So if a method has a certain order, so say the error decays like tau to a certain power, then I would get a straight line when I'm choosing different taus, because the errors would then decay according to this rule. So I would expect here that the error decays along straight lines. I compare here different methods. The green one is an exponential integrator. The blue one is this first order least splitting. The purple one is Strang splitting. I did not really introduce Strang splitting. Well, for those who have never seen Strang splitting, it's a symmetrized version of least splitting, so normally this is a second order method. And this red one is a new integrator I'd like to introduce in a few minutes. So I've drawn here also 2 lines. So these are lines of slope 1/2 and 1. So what I would expect is that the least splitting, the error of the least splitting decays along that line. The error of Strang splitting should decay maybe along such a line, because it should be second order. So both of these splittings the errors don't decay in the right way, whereas a new method that I introduce is apparently first order here. And also the exponential integrator is very bad. So the error behavior is more regular, but still very bad. So the order maybe is here 1/4.
At what time was that error measured?
But the error is measured at time equal 1 or 2, so short time.
Short time.
It's a short time.
And initial conditions?
Sorry?
Which initial conditions are you taking?
Well, this I explain now. So now I have 4 different pictures. What I'm doing in this picture is the following. I'm always measuring the error in H1. So I'm taking a one-dimensional problem, and therefore H1 is an appropriate space to measure the error. So the error is measured in H1, and I'm using initial data that lie in spaces which are a little bit more regular. So this data here is the Sobolev index of the space. So here the initial data are in H1.5. So I have 1/2 additional derivative. Here the initial data are in H2. So I have 1 additional derivative. And you see, in these cases, the classical splitting schemes are very, very bad. If I increase now the regularity, that equals 3, so 2 additional derivatives, then Lie is fine. Because I said before, Lie requires 2 additional derivatives, and then Lie gets fine. But Strang is still bad. If I go to delta equal 5, 4 additional derivatives, then all methods are fine. This is the classical theory. Now, another interesting thing here is that, well, it looks as if our method gets worse when I increase here the regularity, but this is not true. Let me go back, and you will see our method has always the same accuracy. So for this step size here at the end, the accuracy is something like 10 to the minus 4, a little bit better, and it stays. So it's completely uniform. You see? It's just that the other methods are getting tremendously better if you have enough regularity, but our new integrator stays as it is. So the purpose of the talk, and I have still 40 minutes, is to explain a little bit some of the ideas. Well, I have a lot of material here. I certainly don't show all to you, but I'd like to explain a little bit the ideas which are behind these new integrators. Maybe also some small drawbacks I will show. And further ideas at the end on which we are working at the moment. So, well, this is not the program for this afternoon. It's just what I could show to you, but don't be afraid. I will finish it for both. No. But I'd like to go a little bit through this second chapter here, because here I can explain, I hope in an easy way, the main ideas which are behind these new integrators we propose.
Can I have a question? Are the errors that you showed on those rate of convergence plots, are those errors only due to time integration? Essentially, you're doing spatial integration.
Yes, here it's just time integration, because we have chosen the grid such fine that you don't see the space errors. But you're right in.
But if your solution
But later I'll show you also, for a two-dimensional problem, I'll show you the full errors.
because if your solution is irregular, you have trouble with spatial
I
dispersion.
know. You will see also in the second. Well, in that, then in the second order integrate. Good, so how do we proceed? And well, let's say we are given here this nonlinear Schrödinger equation. So the idea is that we first try to get rid of the linear part. And this, in principle, is very easy. You can do a transformation, and this transformation is also known in numerical analysis since many, many years. It's called Lawson transformation, or Lawson transform, from '67. And Lawson proposed this idea in order to be able to integrate parabolic equations by explicit methods. The problem with parabolic equations is that, at least formally, this transformation doesn't make much sense, because if you carry out this transformation, well, the linear term drops, but in the nonlinearity, you get the operator with two different times, with a negative and with a positive time. So parabolic problems, this would be a real problem to integrate backward in times. Well, if you then rewrite the formula in the right way, you'll still find some integrators that make sense also for parabolic problems. But here, in this hyperbolic situation, it's not a problem at all. And you see, when you go from here to there, you get a differential equation where you have on the right-hand side no unbounded operators. So in principle, this is a better equation. Mathematically, it's a better equation because you don't have unbounded operators. So for that equation, of course, you can again write down the mild solution, and you see immediately the difference. The difference now is that v of the n plus tau and v of the n are always close, because this term is always small. This is always of size tau. You're not close, so you gain something. So this was the first step. But of course, you still have to evaluate the integral. So up to now, we've just done some transformation without writing down any numerical scheme. Well, for evaluating the integral, for estimating the integral, you have a second obstacle. I didn't tell you about that previously. So the first thing was you need additional derivatives in the solution to get the order. But the second thing is, at least when you want to work in Sobolev spaces, you also have a sort of barrier. Namely, the Sobolev index always should be larger than dimension over 2. You need this, this is an implication of Sobolev embedding, and you need this in order to estimate these terms here. properly. You want to estimate the term in the HR norm, and this is a product of 3 terms. And for this bilinear estimate, which is given here, you need that. So this is again something which well, creates problems because, for example, in dimension 3, this is 1.5, but I want to go down to L2. So there's still a lot of space between H1.5 and L2. So how to bridge that? Because then I lose this property. But let's assume for the moment that this is not the problem. So we have that, then this term can be easily estimated. Everything is fine. So here's written again what I said already, that the 2 objects here are very close because this is really something small, size 12. Well, in order to approximate this term, well, if you want to have just a first order method, it seems to be sufficient to evaluate the unknown solutions, which you have here under the integral, to evaluate this just at initial value. This is the first idea. So we are doing that. So we take here, we are taking it just initial value. I call the whole integral I. Then we have that. So we are simply left with approximating here an integral. And now, well, the idea could be take an exponential integrator. If you're doing that, you're back to the old problems. You're completely back to the old problems. So you have to do something more clever. And well, from the analysis, then it comes out that the problem of these exponential integrators and splitting methods, they come from the fact that you do not consider in the right way the resonances. So you have to resolve somehow these nonlinear resonances that are in the solution. So how can we do this? Well, we compute them. You said yesterday, if you have enough money, you can do everything. So we go to Fourier space and compute them. You said. So we consider this to be Fourier space. So this integral here, which is written down once more here, we compute it by inserting the Fourier expansion for W, and well, maybe I didn't tell you in the beginning, so I'll tell it to you now. We are solving this equation of the torus. So we have here this Fourier series. This is the expansion of W, the torus. So I take this, insert it here 3 times. You have 1 and here 2 additional. Well, if you have not the cubic but the quintic, you have to insert it 5 times. So for each equation, you have to do this calculation once. You insert it here. You multiply everything out. You collect the terms. You get this. So this is an easy calculation. And it's also clear that at the end, in principle at least, it would be possible to integrate this primitive for the exponential. It's well known, it's again the exponential. But there are several problems here. The first problem I put in red. These are so-called resonances. Now when you integrate this, the blue term gets into the denominator. And of course, depending on the choices of the various k's, so the k1, k2, k3 are the Fourier coefficients of these 3 w's here. Depending on the choice, you can get zeros. So these are resonances. It's bad. You have to, of course, work out these resonances. But the other problem is that when you just integrate this, you get something which is then a triple sum, and then over the dimension. So this is just one dimensional, but you have also dimensions. So this is an enormous row of sums, and you have to compute this. So this is very, 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 very expensive. So this you simply can't do. So the thing is that you have to be able to transform the result back into physical space in order to interpret the result correctly, and then you can also compute it. You will see what comes out. So this, of course, is maybe the step in the right direction, but you cannot do it this step as suggested maybe by this formula. You have to introduce here an additional simplification. And the simplification is that you replace this term by something which gives a nice result and a remainder which you can estimate. And now the question is, what is the something you should keep and what is the remainder? And I think, well, for me in the beginning it was not clear, but after working some time, it became clearer and clearer. Of course, I have to keep this k1 square term, because k1 square means that I differentiate, k is the Fourier coefficient, I differentiate the first function twice. Whereas the k1, k2, well, it's also second derivative somehow, but it's different because here the first function is differentiated once, and the second function is differentiated once. So at the end, in my error estimates, I just get first derivatives instead of second derivatives. So this is the dominant term. So I keep this, estimate these terms here. But this is easily computed. It's this phi1 function, or exponential over 2ik1 square. And, well, same as on the next slide, so I can go directly to the next slide. So the first term I can easily compute. And now you see I get here a formula which at first sight looks a bit complicated. But again, I can evaluate this with fast Fourier transform, and then everything is very easy. Because whenever I have such operators, differential operators, I do this in Fourier space, and there I have diagonal operators. And all the other terms, these multiplications here, the square and then the multiplication of these two functions, this I do in physical space. So I transform forth and back with fast Fourier transform, which is cheap. And then for the remainder now, as I said, I have only first derivatives. Just consider the case gamma equal 1. I have here tau square in the remainder when I have one additional derivative. So if I want to, when I want to measure the error in HR, I need that the solution is in R plus 1, because I need this one additional derivative. I said previously, I go back once more, because this is an important point here. So I need one additional derivative in the first, one in the second, one in the first, one in the third function. This is the key point. Well, then everything is done, so I can make the transformation. I can transform back and I get a formula for u. So this is now my integrator, which, by the way, is very close to the standard exponential integrator. So this is the new integrator. This is the standard exponential integrator. Very close. You have to look twice to see the difference. But this makes a big difference. Well, now I think I skip a little bit of the material because this can be done for arbitrary p and in arbitrary dimensions, but somehow clear. Then you have to analyze this, but this is all standard and maybe not so interesting. And the local error we just looked at. So we get a convergence result saying that whenever we consider this a cubic nonlinear Schrödinger equation and want to estimate the error in HR, as long as the solution is in HR plus gamma, with a gamma between 0 and 1, I get order gamma. This we can prove. And well, again, some examples. Basically, similar examples we have seen before, but now I take the quintic nonlinear Schrödinger equation just to show you that this is not something special for the cubic one. And well, for the quintic here, I have 1/2 additional derivative. You see here also the new integrator is a bit weird, because in the previous example, it looked as if the new integrator even needs less regularity, but this is not true. So half additional regularity is also for the new integrator not enough. You see here some order reduction, and then here's some irregular behavior. One additional derivative, fine, well, and so on. So this is as before. Well, in some situations, you can do better. For instance, for the quadratic nonlinear Schrödinger equation, which is not integral, but it's much better for us. Funny. But for the quadratic nonlinear Schrödinger equation, when I'm doing this approximation in Fourier space, I do not have a reminder. I can integrate everything exactly. And therefore, the methods behave much better. So for smooth initial data, it looks like that. But for random initial data now, even for random initial data now are integrated. This we cannot prove, but for random initial data, our integrator is still first order, whereas Lee and Strang are very, very bad. So this is, again, a half here. And by the way, this is something I didn't mention in the beginning, but if we have small nonlinearities, so the factor in front of the nonlinearity, if this is small, then the new integrator also profits a lot from that. This is due to the fact how we constructed the new integrator. And you see even for smooth initial data, also the new integrator is just first order compared to Strang, which is second order here, but the error constant is much smaller, so you profit a lot.
So in which dimension are those?
No, this is just in one dimension.
Okay. And in higher dimensions?
So
for example, do you think in 1D for small dispersion KDV, this would be better than conventional time integrators? Because then you have a small nonlinearity.
Well, there's a paper by Katharina Schratz who has done a similar approach for KDV. And she shows that her scheme is much better.
Ostermann over Schratz
Mm-hmm.
with Ostermann over.
Sorry?
Oh,
Yeah,
There is a
no,
code.
yes, there's a code.
Alexander, why is the exponential integrator somehow behaving more regularly than the splitting ones? The green line
Here,
always seems to be
irregular.
rather straight, right? No oscillation. It's bad, but it's constantly bad, while the
But here
Nicely made.
we didn't analyze it. Well, we didn't analyze why the strength still shows something. So here, let me see, the slope for the non-smooth is again 1/2 and 1. So we have here still some order, whereas the exponential integrator has nothing. This is, I think, the first equation I've ever seen where the exponential integrator has order 0.
Looks to be negative now, and noise is exactly 0.
I think this is exactly
If
0.
you go long enough, if it's
Well, I
negative.
don't know, but long enough, then you have to use more modes, but this looks pretty much 0.
Long enough and high enough precision, you would get.
A lot of effort to get no precision. Yeah. But this can be extended to second order, and the idea is the same, so I can be also short here and just show you the results. So the idea is, again, that you twist, but now you have to develop one term further. Then you have to approximate this first integral, which in the first order integrator we approximate by a simple approximation more carefully. You carry this out, you're doing again the analysis. You see that now the integrator has 2 terms. They look very, very complicated. But again, it can be computed in Fourier space. You have your operators that work in Fourier space, you have products in physical space, you have some corrections which are due to these resonances. This is more expensive than strength splitting. It's maybe 3 times or 4 times more expensive than strength, but not that expensive as it looks as now. Well,
So
you get.
Here you keep in the second derivatives like before, and you are okay with the first derivatives, or is it
No,
changing again?
I explain now.
Oh,
So
sorry.
what we now need 2 additional derivatives. So we pay a price. So the original strength splitting required 4 additional derivatives. Now if we keep 2 additional derivatives, then we can go up to second order. This is the result we can show.
And you can see it in the previous formulas like you showed us before.
Not so easy. No.
Not so easy.
It's really a long calculation. And well, this is one of the drawbacks of these formulas. In principle, for each equation, you have to do again these calculations in Fourier space because they change. The resonances are not the same for all equations. Each equation has its own resonances. So, let me show you results. So this is now the result for second order integrator, smooth initial data. Well, here I show now the full error, not just the time error, but also the space error. So these small numbers here indicate how many Fourier coefficients I have used. So I enlarge here, or increase the number of Fourier coefficients here by 2. And then I expect that the error decays like 16, so 2 to the minus 4, 1 over 16, because this is the regularity of the solution. So I do not have here this exponential convergence. Convergence of the form. So this is well expected. The Fourier integrator behaves very well. So this is second order here, this slope. So I have a decay in the error until I get saturation, because then I see just a spatial error. It doesn't matter whether I take smaller and smaller time steps, because the spatial error dominates. Strang splitting is more or less the same here. A little bit irregular. I would say still order 2 at the limit, but still order 2. Well, if I reduce the regularity, so instead of now having 4 additional derivatives, I only have 2 additional derivatives, so the initial data are now in H3, and the error is measured in H1. The new integrator still is fine. Back here you see what you mentioned before. Now I need many more Fourier ones. So it's clear, because the error decays slower when the solution has less regularity. So instead of, I think in the previous slide it was 128, now I'll take you almost a little bit more than 4,000. And you see again that Strang has problems, has a lot of problems. And well, here maybe you do not even see all the problems, because it's so irregular. This is also a problem, annoying thing with Strang, that for some step sizes the solution is very good, and for others it's very bad. And in order to see this better, I'll show it to you now once more in a graph where we have taken enough grid points in space so that you do not see the spatial error. So the spatial error is really below. And then you see here the behavior. You see that, well, for certain step sizes here, Strang is still second order, but for other step sizes, Strang is first order. And this is the annoying thing.
Is this growing with the time integration?
Hmm?
If this gap is growing with along the time integration, if you integrate for a longer time, is this difference bigger or?
No, it's always the same. So again, the plot is here measured in H1 and the data H5. So 4 additional derivatives, 2 additional derivatives, 3 additional derivatives, 2 additional derivatives, and shifted where I measure the error in F2.
And these results are independent of the dimension.
Yes.
But if you needed 4,000 modes in one dimension, you'll need 4,000 squared modes in 2 dimensions, right?
Yeah, but
So
if you have a very irregular solution, this is of course the price you have to pay. It would also be interesting, but nobody from physics, I think, is here in the audience. It would be interesting for me also to hear once how much people in applications are really interested in this non-smooth initial data. This is sometimes a mistake we make when, as mathematicians, that we find something interesting and then we develop a theory for that. And we forget to ask whether this is really important for people in applications.
You're answering the question yourself.
Yeah, sure. Well, this is another drawback of our new integrators. So the classic integrator, Strang splitting, is preserving mass. And mass preservation is very important in nonlinear Schrödinger equations. So what I've drawn here is this now, well, I wouldn't call long time, but longer time integration up to time equal 1000. Here, the scale is 10 to the minus 6. The step size is 1 over 100. So I'm carrying out many time steps. And the energy for Strang splitting is conserved. So it stays as it was in the beginning. Whereas we have a linear drift for our new Fourier integrator. And now we can discuss 2 things. First of all, how to prove this. This is not completely trivial. We have specialists here. I'm looking to you, Herman. But this is not completely trivial. And second, is this really a big drawback because the difference is very little. So for long times, 10 to the minus 5. Or if I take a smaller time step, so the error seems to be a constant times the time step to the power of 3, something like that. So it's not enormously large, but of course you need smaller time steps in order to be able to integrate a certain time. So this is a topic here, and the same is true for the preservation of energy. Well, strength splitting also doesn't preserve energy, but at least it remains bounded. You see, it remains bounded. Whereas our new integrator again has a linear increase, but again, on quite long times, the increase is not that much, so it is 10 to the minus 9, but it's linear, I have to confess.
A question, if you, for completely integrable systems, you have a whole hierarchy of these invariants, but they depend on higher derivatives, so they, so what happens in your case when you have lower regularity solutions? Are you defined?
I don't know. Well, this can be extended to other dispersive problems. This is not just something which works for the Schrödinger equation, but in principle works for all dispersive equations. I've done with Chunmei the work on the good Boussinesq equation. And here, excuse me, Chunmei, that I don't have time to explain now everything. I'm really very short. So the good Boussinesq equation, second order problem, where the differential operator is here, fourth order differential operator in space. Well, we do basically the same. So we reformulate it as a first order system and then are doing such a twist, as I called it before. So I eliminate somehow this linear operator. And we then end up with a first order problem. And when we eliminate this operator just by taking here the minus the Laplacian, and this can be computed in Fourier space, so when I take this bracket operator here and subtract the Laplacian, I get something which is bounded, so this A is a bounded operator. So I'm doing basically the same. In the previous experiment, this was even 0, now it's just a bounded operator, so a slight difference, but it's basically the same. So I carry out the same program with a lot of calculations. After some pages of calculations, you find this integrator here, which again looks very complicated, but indeed is not so complicated because again you can use fast Fourier transform to implement all this, and then it's again by a factor maybe 5 more expensive than standard integrators. And when I'm doing, well, here is the theorem. I should at least show the theorem. So the theorem looks very much the same as for Schrödinger. So when I measure the error in HR, I have additional regularity, then I can get the symbol. And for smooth solutions, the integrator behaves very well. So we have a first and a second order integrator. And for non-smooth solutions, it's again very dramatic. So this is now this new integrator, first order. And this is a standard Gaussian first order integrator, which is in the book of Ernst and Christian. And you see this Gaussian integrator, it's a very strong order reduction down to a quarter. Whereas the new integrator, well, nicely I would say, but you have here a few small humps, but this still is bounded, so it's first order. And you see here a huge difference in accuracy. So it really pays off, even if this new integrator is more expensive. But as I said, it's a mega factor too, so about 5%. So it's not that much. Whereas for smooth solutions, so here I have one additional derivative, here I have two additional derivatives for smooth solutions. Both have the same order, 1. Still a new integrator is more exact. So it gives more accuracy. This is a benefit. There is also something very nice with this new integrator. So for this new integrator, we can even show convergence without additional smoothness. So this is very rare that whenever your solution is in HR, you can measure the area in HR and get some numerical convergence. So we do not need additional derivatives. This, as I said, is very, very rare, but this can be proved here. And this relies on an estimate which I didn't know before, but there was a very nice reviewer for this paper, and the reviewer told us about the same estimates. So the same estimates, they look like these bilinear estimates, but you have two different indices on the right-hand side, one smaller than the other, and if you have your functions where the first elements are all 0, then you can compute one norm in terms of the other norm, and you get some extra powers of n out, and with this you can improve your convergence by separating the low frequency and the high frequencies. So it's a bit complicated to carry out. I don't show you the details, but there you can then even show some convergence without additional regularity, which is very nice. Well, in the last 5 to 7 minutes, I'll show you 2 additional ideas very shortly, so I do not go into details, that can be applied in order to break now this barrier R theorem. So I had the barrier when I'm working in Sobolev spaces that the Sobolev index R has to be larger than P over 2. P is the dimension. And this prevents me from going down to L2, to H0. So the question is, can we break this barrier? So can we get even convergence results for very rough solutions? And well, in analysis, there are several techniques known. One are Strichhardt estimates, and the other techniques are Bouguin spaces. And well, both can be used also here. The application is not completely trivial for somebody working in numerical analysis, because you have to read a lot of analytic papers, complicated work. So first is Strichhardt estimates. So the Strichhardt estimates, they are somehow similar to a concept that I used a lot in my previous research in parabolic problems. And in parabolic problems, you have this parabolic smoothing property, which is something really fantastic. Parabolic smoothing means that the semigroup with the Laplacian has a smoothing property, meaning that even if your initial data are very unsmooth, after a very short time, so almost immediately after 0, you have the full smoothness. And this can be proved here very easily. It's a very important tool, and it helps us in numerical analysis to show some superconvergence for methods. So methods behave much better as they should behave due to the effect. So the question is there something similar for dispersive equations?
What's the LRX now?
LR. So this is LR, so X is the space variable, and LR is just LR. So
what's the Lebesgue space?
Lebesgue, yeah. Lebesgue. So we can think R equal 2 if we wish. So the thing is here, even if you have a very irregular function, so you have minus Laplace to the 7th times L2 function, so you have some distribution, very rough. We apply the semiflow of the heat equation. Immediately, the result is L2, but you have to wait for it, so you get a singularity here. But if time is sufficiently large,
you mean the other way around? You start with a function that's L2, and immediately it has a Laplacian. It's in a Sobolev space.
This is another way of seeing it. Yeah, you can see it in both ways. Why not? You start with very rough initial data. You start the heat equation with a distribution. And then you solve, and immediately the solution is smooth.
Right.
Yeah. Okay, so is there something similar for dispersive equations? And well, the answer is yes. There are the so-called Strichhardt estimates. And the Strichhardt estimates, well, they are a bit complicated. in the sense that they are not pointwise in time. So whenever you want to estimate here the evolution operator applied to a function in LP with respect to time and LQ with respect to space, we can bound this by the L2 norm, but these indices P and Q, they have to satisfy something, some admissibility. So this is not for free. And well, as I said, they are not pointwise in time, and these Strichlatz estimates also do not hold for time or fully discrete problems. So it's not just that you take these Strichlatz estimates and say, now I apply it to my numerical scheme and I can prove everything. It's a bit more complicated. What you have to do, you have to consider filtered function or filtered equations. So you have to take a cutoff of the high frequencies and analyze first the equation where you take this cutoff. And for such problems, then you can find discrete Strichlatz estimates. And then when you estimate the error of your discretization, of course, using Strang inequality. So you estimate the error of your numerical solution with respect to this exact solution and then the two exact solutions. This is done. And then you get these discrete Strichlatz estimates. Well, I do not go into details here. They look complicated. And if I should explain this, I think I would need another hour really to explain all the details. But what we can then prove, and this is work together with Katharina and with Frédéric Rousset from Paris-Sud, is that depending on the dimension, we really now get L2 estimates whenever the solution is just in H1, and you get certain orders. So delta is the order of convergence. So this is an improvement. This is not an improvement in one space dimension, because in one space dimension we can go already with the other techniques down to a half almost. But in 3 space dimensions, this is an improvement, because in 3 space dimension, the barrier of the suborder spaces, the barrier is 1.5, and now we can go down to H1. So already an improvement. But I think we can do better, and for doing better, one has to use still another technique, which goes back to Bourgain and others. I can't explain here much. I'll just tell you that instead of the Sobolev spaces, you're using now different spaces, which are meanwhile called in the field Bourgain spaces. And these Bourgain spaces, they are obtained by, well, you take your function that depends on time and space, you do a Fourier transform, and then in Fourier space, you take here this weighted norm. So with respect to k here, so k is the x variable, it's a torus. This is just a standard Sobolev norm. But here, with respect to time, you have a certain weight here. These are these Bourgain weights. The nice thing is that when you then consider your bilinear estimate, you want to estimate now this product of the 3 terms in these Bourgain spaces, you can do this. You can do this even when the first index here is now 0, which relates to the fact that actually you're working in L2. So you can now work in much rougher spaces with respect to the x variable. And well, Bourgain and then others, they were able to show that when you take initial data in HS, s greater equals 0, even they can go to negative s, I think up to s minus half they can go. They can prove that the nonlinear Schrödinger equation has a global solution. So these are the results we can rely on. And then what we have to do, we have to transform this into a numerical method. And what one has to do, one has to construct discrete Bourgain spaces. One has to prove properties of these discrete Bourgain spaces, which are similar, analog to the properties of the Bourgain spaces. You again have to use filtered function. This is just one result. We also have results where you filter each of these factors with different filter functions, so it gets quite involved. But then we can go down to L2 and can show convergence for very small exponents of Sobolev spaces. So if the solution here is in HS for s greater than 1/18, so this is already very close to 0. It's very irregular. We still can prove convergence of a method. So this is where we are at the moment. Well, I think with this I can almost close. So my talk was about time integration for dispersive equations, and what I've shown you in the beginning, and this is something maybe, I'm sure that you will forget most of the details I've shown to you, but maybe you remember that you have to be careful with standard integrators for solutions which are not very regular, because the standard integrators have a tremendous order reduction. And there are now new integrators that require less regularity. And for analyzing this, well, you can work with solar spaces, but they have some limits. And if you really want to go close to L2, you have to use this Richard's estimates of Boussinesq spaces. Thank you very much.
Okay, we have time for a few questions. So let me kick off. Going right to the beginning, you have this asymptotic expansion, and you don't have a problem of small denominators. I agree that you don't have a problem with regard to derivatives, because K1 corresponds to the rough stuff and the rest are very smooth. But still, 1 over K1 square minus K and so on can be not 0, but can be very, very small.
No, but this we estimated. So whenever it is in the remainders, we really estimated this.
I see.
And whenever it is in the formula itself, then we do these corrections to the formula so that we evaluate all these terms which tend to give problems. We evaluate them then by using some Fourier coefficients. So this is reflected in the formulas. And so there is no problem with that. We were very careful about that.
So let me ask first, with your initial data that's rough, where is the roughness coming from? What is the nature of the...
Sorry?
What is the nature of the function that makes it only in the Sobolev space h a half or h3 halves or something?
Well, this is related to the question I posed myself during my talk, whether our people in applications are really interested.
So in spatial discretization, it's very common that you have a solution that's only in h3 half, say, and yet you have a method that converges to the fourth order or more. But that's achieved with non-uniform meshes, with some sort of adaptive meshing. With adaptive meshing.
Yeah, but then you know already where the singularity is. So for instance, when you have a corner, you get singularities in the corner, then you adapt.
Or if it's adaptive meshing, your program may find the singularity itself. That's the goal to do it. Of course, it doesn't apply to a general function.
No, but here it's not a function of singularity, it's really a rough function. So saying that the Fourier coefficients, they do not decay properly.
Okay, well then it does come a question like that. In my experience, rough functions almost always are piecewise analytic. They're rough in some places in the domain. Certainly there's many such functions like that.
No, this is certainly a good question. I think we have to discuss this with people from physics, whether this is really an issue for them.
One obvious example is the turbulent effect.
In turbulence, they have
Turbulence, okay.
You take a grid and you put some random forcing or random initial data at each grid point with a small correlation, and then you end up with something like that. And what they do is that they average. So in order to average, so to calculate the expectation, of course, if you have an integrator that is good at this level of regularity, so in the context of turbulence, I guess
Then, as you say, you're going to need giant numbers of Fourier modes to deal with functions like that. And let me ask one more question. Suppose instead of being on the torus, you were on a pentagon. And all these Fourier space goes out the window, right?
Yeah.
You cannot generalize to that.
Yeah, but that's the thing you've done in the time.
Not for the moment.
What's that?
The thing that the estimations you're just doing in the time domain, so the first part is just one.
Well, but you're always using the operator e to the I Laplacian.
But you have to
you have to
compute the objects. Yeah. Of course, you can
When I
write
think
them.
of solving the spatial equations, I always think of working in physical space and in grid and sparse matrices and so forth. You're in a different world here.
Yeah, but if you are in a pentagon, you have a budget of $1 trillion.
You had a question about whether the parabolic stuff carrying over to the dispersive stuff.
Well, formally, just.
Yeah.
Of course, this doesn't really carry over the distance.
Well, there's a result by Percy Dieft and somebody.
This was here.
Right, there's a result by Percy Dieft and somebody, and I forgot the details. But if you start off in a certain non-smooth initial condition, immediately your function becomes analytic.
Yes, for
And
parabolic, yeah.
No, for KdV. This was particularly for KdV that I'm thinking. So is there any use for that particular analysis?
Well, I don't know this paper. Maybe you can give me a reference.
I'll find it. Yeah.
When it comes to this rough initial data, I would somehow expected that you will start averaging at some point. But you didn't, right?
No,
Your error measure is a Sobolev norm at the end of your analysis. Wouldn't it also be interesting to look at moments of your solution and see how they
You're
react?
completely right. Yeah.
Should give you maybe a better life.
Yes.
Okay, last question. In analysis of nonlinear Schrödinger, small solutions play very important role. So people can prove things for small solutions. But here, this is not a problem.
No, because this was, so the last slide was for the defocusing Schrödinger equation for a certain range of this piece I quoted previously. So it becomes an issue when you take other exponents or other dimensions. Then, of course, this can also be an issue. We didn't look up into that. I'm aware of the fact that small solutions quite often are important to get long-term existence.
Okay, well, thank you.
Okay.